So up to now we have seen about the magnetic effect of the electric current. There we have studied about the magnetic field produced around the straight current carrying conductor. Now the next part is that is the right hand thumb rule. So this is a convenient rule for finding out the direction of a field produced by a current flowing through an electrical conductor. Imagine that if you have held the conductor in your right hand in such a way that your thumb points in the direction of the current. Then turn your fingers around the conductor. The direction of the fingers is the direction of the magnetic lines of the force. So what they have told here that we have to take a current carrying conductor that holding in our right hand and as shown in this figure. So the direction upward, that is the thumb direction, is showing the electric current, and the curled fingers are here showing the magnetic field produced by the current carrying conductor. So magnetic field produced by a current through a circular loop of a conducting wire. We learned about the magnetic lines of the force of a magnetic field produced by the current flowing through a straight conductor. What will happen to the magnetic lines of the force of the field produced by a current flowing through a loop made by bending the straight wire? So again we are given here one activity that we have to perform. A circuit is completed by connecting various components as shown in the figure 4.8. If the current passes through the loop, magnetic lines of the force are produced at each point on the loop. As we go away from the wire, the concentric circles representing the magnetic lines of the force will become bigger and bigger. As we go towards the center of the loop, the circle becomes so big that its arc can be shown as a straight line. In figure 4.8, the magnetic lines of the force are shown near the points P and Q only. However, they will be created near each point on the loop. Likewise, each point will produce the magnetic field at the center of the loop. By making use of the right hand thumb rule, check that every point on the loop contributes the magnetic lines of the force at the center of the loop, and these lines of the force at the center of the loop are in the same direction. So, what here, as this experiment which we have performed here, we have taken the iron fillings, and that are fillings are spread on a cardboard, and we have made the connection of the circuit here, and as the current passes, the magnetic line, the iron fillings get formed in the concentric circles. So that they are showing that the magnetic lines of the force. So again we have seen in the experiment that of the magnetic lines of the force. So here the due to the electric current, the magnetic field is generated. That experiment also state that. And here the same experiment we are doing, but here we are what we are taking, that we are taking a conductor loop, and that conductor loop we are making it connection with the in the circuit. Here is the rheostat, ammeter, and here is the battery. So as the current gets passes through that straight current carrying conductor, as per according to the right hand thumb rule, so we can find out what are the direction of the what is the direction of the flow of the current, and what is the direction of the magnetic lines of the force. So as we can see here, the magnetic lines of the force are generated here, and the direction can be find out as the current is flowing in the upward direction of this. So as per the right hand thumb rule, so the curled fingers will show the magnetic lines of the force direction. So as we can see here, and as what they have stated here, that when we move, as we can see here, the magnetic lines of the force are in the concentric circles. But as we move from away from the current carrying conductor, so the magnetic lines of force will goes on increasing in the size, and at the one end of the point that it will become a straight line. So this was the experiment. The intensity of the magnetic field at any point produced by a current flowing through a wire is dependent on the current. As we have seen in the experiment 4.6, try this. So the experiment, that is the 4.6 which we have seen here, basically stating that only the intensity of the magnetic field. This means that if there are the n turns in the loop, the magnetic field n times of that produced by a single loop will be created. So, as there will be the n turns in the loop, so as the number of the turns in the loops will goes on increasing, suppose they are taken to be the n turns, so the magnetic field produced, so the intensity will of that particular magnetic field will be also goes on increasing. On discussing with your teachers with their guidance, see if you can perform the above experiment by collecting appropriate materials. The direction of the magnetic field can be determined with the help of the magnetic needle. Magnetic field due to the current in a solenoid. So we have to see this. When a copper wire with a resistive coating is wound in a chain of the loops like a spring, it is called as a solenoid. So this may be asked in the exam regarding with the solenoid, how the magnetic field is produced. Whenever an electric current passes through a solenoid, magnetic lines of the force are produced in a pattern as shown in the figure 4.9. So as we can see here, the solenoid coil is made a connection of the circuit here with the help of the solenoid coil, and we can see here the magnetic lines are generated here. So, whenever an electric current passes through a solenoid, magnetic lines of the force are produced in a pattern as shown in the figure 4.9. You are aware of the magnetic lines of the force of a bar magnet. So, the magnetic lines of the force which are generated as in the with the help of the bar magnet, we have studied this about in the class 8. So the properties of the magnetic field of a solenoid are very similar to the magnetic field produced by the bar magnet. So as we have studied in the class 8 that the magnetic lines of the force which are generated, suppose here it is the bar magnet, that is the north and the south poles. So the how the magnetic lines of the field of lines are generated like this. And this was basically the direction of the magnetic lines of the force which are generated. So similar kind of the magnetic lines of the force are also generated when a current passes through the solenoid coil. One of the open ends of the solenoid act as a magnetic north pole and the other as the magnetic south pole. The magnetic lines of the force inside the solenoid are parallel to each other. What does this mean? This means that the intensity of the magnetic field within the solenoid is uniform everywhere. This is the this question asked in the exam many of the time in the complete the following activity, that the this means that the intensity of the magnetic field within the solenoid is uniform everywhere, in that is the magnetic field in the solenoid is uniform. So next part, that is force acting on a current carrying conductor in a magnetic field. So again, we are given here one experiment: materials, copper wire, stand, electric cell, horseshoe, magnet with a strong magnetic field. Procedure: using the stand, fix the copper wire so that it passes through the poles of the horseshoe magnet as shown in the figure 4.10. Like this, we have to perform the experiment. Connect the circuit as well. What do you observe? Whenever a current is not flowing through the wire, it remains straight, position A. So as we have to perform this experiment, that we have to take one horseshoe magnet, put it in the stand, and one straight carrying conductor, uh, attach it with the another stand. So as there is a no current flowing through this, so the straight conductor will be in the straight direction as the position A states. So here we can see the position A, that is it in the straight direction. So If the whenever a current is not flowing through the wire, it remains straight position A. When the current flows from the top to bottom, wire bends and comes into the position C. So as the current flows from that current conductor, so the straight current carrying conductor will change its position as it will bend, and this we can see here in the position C. So if the current direction is reversed, that is, it flows from the bottom to the top end, the wire bends but becomes in the position B. Or if we are changing the direction of the current, if we are reversing the direction of the current, so the straight current carrying conductor will bend towards the position B, as we can see in the figure 4.10. So here the direction of the magnetic field is from the north to the south. In this experiment, it is noted that whenever current flows through a conductor in the presence of the magnetic field, a force is exerted on the conductor. If the direction of the current is reversed, the direction of the force also gets reversed. If the magnet is kept reversed, that is, the south pole is brought at the position of its north pole, and its north pole brought to its position of the south pole, what will happen? The above experiment clearly shows that the force is exerted on the current carrying conductor. The direction of this force depends on both direction of the current as well as the direction of the magnetic field. So from this we can state that the force which is exerted which is acting on the straight current carrying conductor will be depending on, that means it will be directly proportional with the direction of the current which is flowing through that current carrying conductor, and also depends on the magnetic field which is generated here. Experimentally, it is possible to show that this force is maximum when the direction of the current is perpendicular to the direction of the magnetic field. How will you do this? So, magnetic field perpendicular to the plane of the paper going inside the paper. So, next is the Fleming's left hand rule. Again, the Fleming's left hand rule and the right hand rule are basically the most important with the exam perspective, as it may ask in the brief question answer. So again, it can be asked in the activity, complete the following activity, as this diagram will be given in the exam, and here the boxes will be there as we have to fill this with the proper labeling. So Fleming's left hand rule. In the above experiment, we considered the direction of the electric current and the direction of the magnetic field, and found that the direction of the force exerted is perpendicular to the both. There is a simple rule relating these three directions. This rule is called as the Fleming's left hand rule. According to this rule, uh, the left hand thumb, index finger, and the middle finger are stretched so as to perpendicular to each other. If the index finger is in the direction of the magnetic field and middle finger points in the direction of the current, then the direction of the thumb is the direction of the force on the conductor. So according to this rule, we can able to see the force acting on the particular conductor, that in which direction the force is acting on the current carrying conductor. So here the index finger is basically showing the direction of the magnetic field. Then the middle finger is showing the direction of the current, and the thumb is force on the conductor. So this rule is basically used in the application of the electric motor. So you know various forms of the energy. You also know that energy can change its form. A device changing electrical energy into mechanical energy is known as the electric motor. So electrical motor is basically the electrical energy is converting into the mechanical energy. As we have also studied about the energy conservation law in the class 9, that energy can neither be created nor be destroyed. It can be only converted from the one form of the energy into the another form of the energy. So here, that is, the electrical energy is getting converted into the mechanical energy. Around us in our day-to-day life, an electric motor is a boon. It is used in the fans, refrigerators, mixers, washing machines, computers, pumps, etc. How does this motor work? The electric motor consists of the rectangular loop of the copper wire having a resistive coating. As shown in the figure, it is placed between the north pole and the south pole of the magnet, such as a horseshoe magnet, in such a way that its branches AB and CD are perpendicular to the direction of the magnetic field. So basically, what we are seeing here, the application, how the uh, this Fleming's left hand rule is basically applied for the generation use of this electric motor. So we are taken here the two bar magnets, that is the north and the south pole of that bar magnet is here, and we have taken one rectangular coil, so which is named as the ABCD here, and the two ends of the loop are connected to the two halves, that is X and Y of the split ring. So here you can see here the split ring. So X and Y, the two halves of that rectangular coil is connected to that split. The two halves of the ring have the resistive coating on their inner surfaces and are tightly fitted on the axle. So here you can see the axle is there, and on which the split rings are fitted, and on the split rings the rectangular coil is attached. So the two halves of the split ring X and Y have their outer coating surfaces in contact with the two stationary carbon brushes E and F respectively. So here can see the carbon brushes, that is denoted with the E and F here. So, how this electric motor principle works? When the circuit is completed as shown in the figure, the current flows in the branch AB of the loop from A to B through the carbon brushes E and F. So, as the current flows from A to B, rectangular coil, that means the direction of the flow of the current is, you can see here, direction of the current is denoted with the middle finger. So that means the direction of the current will be as such. So the force on conductor will, force of that rectangular coil will be in the upward direction. So in the upward direction, the force will be acted. So the rectangular coil will move in the upward direction. So next, that is since the direction of the magnetic field is from the north to the south pole, according to Fleming's left-hand rule, force is exerted on the branch AB and pushes it down. The current in the CD branch is in the opposite direction to that in the AB branch, and therefore a force is exerted on the branch CD in the upward direction. Thus, the loop and the axle start rotating in the anticlockwise direction. After half rotation, the two halves of the split ring X and Y come in contact with the carbon brushes F and E respectively, and the current in the loop starts flowing in the direction DCBA. So the current will start flowing in the DCBA, that is in the anticlockwise direction, and the loop will the rectangular coil will be moving in the anticlockwise direction. Therefore, a force is exerted on the branch CD in the DC in the downward direction, and on the branch BA in the upward direction. Loop continues to rotate in the anticlockwise direction. Thus, the current in the loop is reversed after each half rotation, and the loop and the axle continue to rotate in the anticlockwise direction, and due to which the force exerted in the anticlockwise direction, as we can see, so the axle will start rotating in the anticlockwise direction, and this will lead to the uh, flow of the current and the acting of the force on that rectangular coil. Commercial motors run on the same principle, but practical changes are made in their construction. You will learn that later. So, why are carbon brushes used? How do this work? In order to find out the answer to these questions, visit a nearby workshop and try to understand the construction of an electric motor. So, this is basically, you can think about that why the carbon brushes are used here. So, the basically the carbon brushes are used for making the contact, as the contact will be loosed, as there you can see here the split ring is having the gap, so to make the coil to rotate continuously, so the carbon brushes are used, that basically helps to make the avoid this gap in of the split ring, and makes to continue the rectangular coil to rotate in the anticlockwise direction.